It is a great pleasure and an honor to have with us Professor Christine SILBERHORN from the Integrated Quantum Optics and Department of Physics and Photonic Quantum Systems Institute at Paderborn University in Germany. She has done pioneering work in several areas of optics and quantum optics and many aspects of quantum optics, and has done exciting work. And today she's going to show some of this great work, and it's a great honor and pleasure to have her here. Okay, please go ahead.
Well, thank you very much for that kind introduction, and thank you very much for inviting me. I'm very happy to talk about our work here, and I entitled it Quantum Photonics Using Nonlinear Integrated Optics and Pulsed Light. That's a rather descriptive title, but I think in photonics, what we're doing right now is really to design multi-dimensional systems. Why is that? Well, one motivation is definitely quantum computation and simulation. I will say a few words in a minute for that. But also the other fields where optics is very suited for, like quantum metrology benefits from multi-dimensional systems, as well as quantum communication, which is clear, because we're talking here about information which is carried by quantum states of light, and orbital angular momentum states, or what I will be calling temporal modes of pulsed light, allow you to have high dimensional encodings. Now, let me say a few words about quantum photonics and quantum computation simulation. I think it's quite fascinating that in 2020, it was actually the photonics platform where quantum advantage could have been demonstrated. And this experiment by Shou-Yang Lu's group and Chan-Wai Pan's group kind of brought photonics back into the regime that we say, yes, we can also do some quantum simulation. Well, you see, this experiment is an experiment which is really, well, a milestone experiment, but it was very difficult already with a lot of bulk elements. This story continues. This year, we saw a paper by the Xanadu group, which basically shows that you can make even larger systems, where nowadays 260 modes and 219 photons are combined to really have their programmable computer. And you see already that they use a different technique. They use time multiplexing, which I want to be talking about later on, which we did for quite some time. But before going really into the talk, I would like to highlight the following. What they have demonstrated is boson sampling, one variant of quantum simulations of the one, and where people have been proven for quite some while that actually this can give you the quantum advantage, or you can design systems, but you can't compute efficiently in a classical computer anymore. Now, for scaling photonic systems, to have single photon interstates is very difficult. Thus, in 2017, I was participating in some work where you think, how can we really make things more practical? And one way to make it practical, which we proposed, was use different input states. And these states were squeezed input states. It turns out if you do that and build up a standard boson sampling system, the famous one, that you also receive a problem which is computationally hard. And this is nice. This is actually systems which are implemented nowadays. For me, that's very fascinating. But it shows you that sometimes experimentalists can also give you an insight how to scale system, because this is really the challenge we're facing these days. What's the next step? Well, the next step is trying to get systems more and more integrated, because this is a way of, if you're talking about photonics, to get integrated systems. And here I show you a review how such an integrated system would look like. You have a source side, which is nonlinear circuitry, a linear circuit, and detectors afterwards. And this is what we're working at the moment. So before going into detail, please allow me to introduce briefly the Integrated Quantum Optics group, which I'm heading. Actually, we are having their different competences, and we have one subgroup led by Christoph Eigner, who really deals with technology, because I really believe we have to build the technology which is really tailored to our needs for quantum photonics. Then you have to go to the optics lab and have to build devices out of that. And there's experts in my group led by Harald Hermann who really focus on building up devices. And last but not least, we also need to have the quantum systems operating, and their theory plays an important role. And we have the quantum networks group led by Benjamin Brecht. What you see here, and this is why I show that to you, is that I think the philosophy has to be that we have to go from theory to technology to building up devices to really, this is what's coming next. So let me briefly give you an outline what I want to be talking about and which approaches we are actually pursuing to get high-dimensional systems. I want to start to talk a little bit about temporal mode engineering. It's important, but also a fascinating field, how you combine pulsed light with quantum optics. I talk a little bit about nonlinear integrated circuits. And last but not least, I also would like to illustrate a little bit what time multiplexing can do for you to get large-scale systems. Temporal mode engineering of pulsed light. Let me start very basic here. If you learn in quantum optics what a quantized field mode is, you very quickly introduce the concept of a monochromatic mode operator. So you say you have your field and then you can quantize this field. Now these monochromatic mode operators can't be reality, as you see immediately. If you do a Fourier transform, you get something which is infinite in time. So it will never be reality because, for example, for quantum communication, that would mean that you have a bit rate of 0. What do you have to do? Well, you have to define something which is constrained in time. And via Fourier transform, you immediately see you have to introduce wave packets. So we introduce a wave envelope function, which is given by the superposition, coherent superposition of different frequencies. And then you have a nice quantum object. And we are working with these wave packets. What I've done here is now that I introduced temporal envelope functions for these things. And if you believe me that I introduced for quantum states a Gaussian envelope function, I can equivalently introduce different envelope functions. And here you see the meet modes. The meet modes are field orthogonal, so they constitute a nice Hilbert space. And if you want to have it less formal, instead of operating with different frequency modes, you could think that every envelope function defines your different mode, and then you can work with them as you're used with spatial modes or elsewise. There's one challenge: these temporal modes overlap in frequency and time, and you have to deal with that. Nevertheless, what we're doing these days is that we have our state preparation. I will go in a minute into that via parametric down conversion. It's the workhorse which we use a lot in quantum photonics. What you do there is that we have a nonlinear waveguide system which we pump per pulse light, and due to that nonlinear action, we're generating signal and Adler photon pairs. But these photon pairs have also spectral temporal properties. Now, if we design our system nicely, these temporal spectral properties can be defined, and we can have the situation that one pulsed photon pump pulse creates a photon pair which is nice pulse shapes. We can go further and we can play with these pulse shapes and define different temporal modes, as I just did at the introduction. And the joint spectral amplitude is the tool which you have to monitor to really see what these quantum states are. And when you can prepare systems, then you can also think, how can we manipulate that? And I will show you in a minute how we do that. Similar ideas like spectral temporal engineering, which were introduced for parametric down conversion, can be used with some frequency generation. And then you can do manipulations on these, and we can overcome the problem that temporal modes overlap in time and frequency. So let me have another look a little bit closer at that parametric down conversion. As I told you already, a pump photon decays in a signal and Adler photon. For this to happen, you have to obey energy and momentum conservation, such that the frequencies of the signal and Adler have to add up to the frequency of the pump, and also the phase matching has to obey, and thus we get a joint spectral amplitude. The way we demonstrate that typically is contour plots. This is frequency of signal and Adler. Here we plot energy conservation. Phase matching means because different velocities, these signal and Adler photons travel at different velocities. We have another contour plot for that, which altogether in the overall process results in a joint spectral amplitude, where you typically will find that this function f omega s omega I exhibits some correlations. Now, if you're talking about these pulsed photon pairs, I want to give you in a nutshell what that really can be interpreted at. I showed you that we want to have one pump pulse creating one signal and Adler photon pulse, but unfortunately, that's not what's happening typically. What's happening is that this pump pulse is actually generating a multitude of different temporal modes, and this is typically called Schmidt decomposition, and I show you what that means. It means the following. We basically can say that, yes, we are generating signal and Adler photons, but in pairs of pulsed modes. If every time if a signal photon is generated in a Gaussian beam, a Gaussian shape, the Adler is also in the Gaussian shape, as you see here, but we have a high dimensional Hilbert space where these different temporal modes which are introduced kind of form a basis of that. This has to be controlled if you want to use this pulsed light for using them in spatial networks. And this is known these times under the term of dispersion engineered parametric down conversion source. So by engineering your phase matching, you can get rid of these correlations. And getting rid of this correlation means in our picture that we really have the situation arrived at the signal I showed you at the beginning, that pump pulse is decaying in signal and idler pulses where you have nice shaped wave functions. We do that in my lab for a PPKTP waveguide at telecom wavelength regime. And these sources which we implement are ideal for networking with multiple spatial channels. You have pulsed light for state synchronization. You can have very high purity and high brightness. The fascinating thing is that you can basically really control the system very nicely. Here you see on the left our experimental setup. What you have to do, you have to adapt your pump spectrum to the phase matching, and then you operate at the single mode behavior. If you do so, you can pump your parametric down conversion sources harder. And up to now, I said one pump photon is decaying in a signal and idler photon pair. Actually, if you look at the Hamiltonian, it's getting more complicated. You're not only generating one pair, but pairs of pairs. And typically, these are considered as p-detrimental. However, the state which is generated stays non-classically. Also, if you pump it harder and harder, it's actually a two-mode squeeze state, exactly the characteristic of states you want to have for the Gaussian boson sampler. So this is where actually the motivation also came from our side. If you then ask how non-classical is it and how efficient can your source be, you characterize them in terms of photon numbers. A single pass photon, a single pass source, as I just demonstrated, can have very non-classical features. We can have up to 20 photons generated for a single pulse. This belongs to really high joint photon number squeezing, and you have a mesoscopic quantum state of light. Here you see work which we did in collaboration with Boulder in 2016. We really could see that we can prove non-classicality for heralded photon numbers up to 50. We continued on that work and now used our source not with the superconducting detectors of Boulder, but really used them beforehand in a time multiplex network. What that does for us is that it separates these pulses out, every single one, and we can then look for click statistics. We basically can look kind of for higher order correlation functions in these systems. And this is results where we have up to 46 mode, which we can show that they share non-classicality in 10 photon heralded states. The interesting thing is to analyze non-classicality in such states in a network, which I just showed to you, you really need statistical methods. And this is where you see that characterizing large-scale systems really becomes a challenge. And here we could characterize and demonstrate the non-classicality of a rather large system. Let me swap a little bit back to the pulse mode. Up to now, I said we want to have one Gaussian pulse and want to control that and want to engineer all modes out. Actually, if you're thinking about different systems and we want to achieve high dimensional information encoding, we really can also use these high dimensional temporal modes for high dimensional alphabet. You might have heard about that for spatial modes. In temporal modes, you have the advantage that you can do the same encoding. You get the same enhancement against losses and noise. You can encode more information per photon. They're natural present from PDC sources, as I just showed you. And in addition, they're compatible with waveguide devices. The only problem is how can we manipulate them? First of all, how can we create them? And I showed you beforehand that we had this PPKTP with a pump pulse, which was Gaussian. We can now play with programming different pump pulses. And with that, we can control very nicely how we actually tailor this Hilbert space in the temporal modes. And this is what we're doing nowadays. The next step then is how can we manipulate them? For that, we invented the quantum pulse gate. As I told you at the beginning, it's a dispersion engineered sum frequency process that is similar to what I presented to you for the PDC to start with. And what we can do now is we have a knob again with a pulse. Now for some frequency generation process, the red photons are our signals, which we want to manipulate. And then we can have like an add drop filter for temporal modes with these pulse modes and do complete manipulation. If you want to read about that, what you can do with that, I would like to refer you back to a paper in 2019, which we had with Mike Raymer's group, where you can say that you can translate all kinds of quantum information processing protocols for photons directly in this temporal mode basis. The pulse gate itself, we also implemented that recently. It's PPLN waveguides with very specific properties, which we can operate again for signal state at 1550 nanometer and pulse shaping at 860. And we can select arbitrary temporal modes in time or time frequencies for push system states. And just as an example, we analyzed PDC states, these temporal modes, and we can basically see that we really can handle this high dimensional Hilbert space quite nicely. With that, because I'm running out of time, I would like to switch gears and talk a little bit about nonlinear integrated circuits. Now, nonlinear integrated circuits, we are interested for that for quite some time. In Paderborn, we're working more than 10 years on this platform. And integrated circuits, I think I don't have to say much about that. You heard about that, that they are really great to scale up photonic system. What do you need? You need really low loss waveguides to minimize decoherence. You have a stable and scalable system. Now, what lithium niobate can offer you, it's a Chi2 nonlinear material that can have very efficient photon pair generation. And maybe more importantly, we have fast photon routing. So we can have fast electro-optic switches. And this is really what's needed if you really want to implement, for example, fast feed forward operations. This is the toolbox, which is in journal available, how I demonstrated. You have generation and storage of states, which can be done in these platforms. You have passive routing like in all integrated platforms. You have the benefit of that active manipulation, which can be fast phase switches, polarization transformers, or also switches in the spatial domain. And interfacing should also be not neglected. For example, you want to have very highly efficient fiber coupling, or also can build up resonators. The technologies which we're developing in Paderborn provides the device basis for PPLN-based linear circuits. Now, I can't go into detail, but we have done all kinds of different integrated systems, plug-and-play single photon states, noon states, generation of polarization entanglement. I always call it like Quiot-like source because you basically can have them degenerate. We have demonstrated free photon states in a cascaded process, optical squeezing using waveguide resonators, narrowband sources. We can combine resonators with integrated modulators, quantum interferometers. The thing which the device I want to show you a little bit more into detail is actually the Hongo-Mandel interference chip, which we demonstrated in 2019. The reason for that is that we see the most functionalities in one single chip. Very briefly, what is a Hongo-Mandel interference? The two photon interference are balanced 50-50 beam splitter. So if you consider that two single photons impinging on a 50-50 beam splitter, you can imagine that this would be classically the four different possibilities. Due to deconstructive interference, we know since quite some while that photons bunch, so they always exit at one output port. This is a very important fundamental quantum property of quantum states of light. It's the basis of all linear optical quantum computation or quantum network in general. The famous Hongo-Mandel interference is you have these photons impinging on a beam splitter, you introduce a time delay and record coincidence events. For building up a technology, we thought it's a good idea to implement this Hongo-Mandel interference on a bulk chip. So what do we need? We need a parametric down conversion source, and we see on the left the bulk optical analyte, and the right how we constructed our chip. We need a polarizing beam splitter. We want to have converters which can be done electro-optically with lithium niobate and adjustable 50-50 beam splitters. Altogether, what we did the monolithic integration of a parametric down conversion source and a two-photon interferometer with a relative time delay. And let me show briefly how this works. So we have a PDC where pump photon is decaying in signal and idler photons. We have here polarization converter. I will explain in a minute why we have that. We split our two photons into two parts. And then we have another polarization converter, which is segmented. What we're exploiting to implement this switchable delay is the birefringence of lithium niobate. H and V photons travel at different speeds. And as you can see here in this illustration, if you switch the segmented polarizing converter at the right position, you get the famous Hong-Mantel bunching, but we can switch it at different positions. And then you see that we introduce effectively at the 50-50 beam splitter the delay. So this is what you would expect, depending which segment you switch, you get your Hong-Mantel dip. If you don't switch at the beginning, you're not compensating the difference at the beginning, and you get a huge delay to start with. This is experimental results. And basically what we could show with that device is that, yes, we had a very high on-chip visibility of over 90% and could switch with electro-optic switching delay times up to 12 picoseconds. This is a very important tool, we believe, if you think about quantum networking in the future, where you really have to synchronize very fast, and you see that electro-optic switching can work nicely in there. Okay, so this gives me approximately 10 more minutes because I want to now go over to time multiple. Oh, sorry, just maybe to give an outlook for this area. All this was done in waveguides, in titanium in diffuse waveguides. And we are now currently developing that in an LNOI platform. This is a very exciting development we have seen and really gives LNOI also the possibility of miniaturization. Okay, with that, I now want to switch again gears because I want to show you how versatile photonics can be and want to talk briefly about time multiplex systems. Time multiplex systems we have been doing for more than 10 years now, because I believe time multiplex is a very efficient way of scaling up photonic systems. One basic principle to demonstrate that it works is random versus quantum walks, and I believe you've heard about that. So a random walk is something which is a primitive for mathematical analysis. So this little walker goes on a Golden board where if imposed, you decide to go left and right, and we can study the output distribution where these balls end up with. We know that it's a binomial distribution corresponding to a diffusive propagation. Now, if you want to see how does that system go quantum, we introduce at every post a beam splitter, and we look at these interferences. The superposition change the dynamics dramatically, such that we can have ballistic distribution. And this is basically to see one network, an interesting network for scaling up quantum systems in the photonics domain. How do we do that? Well, we implemented it for quite some time in the temporal domain and using time multiplexing. This time multiplexing system, so we use pulses again, and we have a double loop structure. You see here the inner loop with different lengths and the outer loop, which kind of allows us to repeat the setup over and over again. So here we start our system at the beginning, we initialize the system, we have a half wave plate, which is kind of the coin operation. Then depending on the polarization, our pulses take either longer or shorter route in this inner loop, and a relative shift in time corresponds then to a step in position space. You go now to the outer loop and you repeat the system again, and what you find is that the system can go either the shorter path of the first round or the second round, the shorter path of the second round, the longer than the second round, or vice versa, and you get there nice interferences. If you repeat that over and over, you get your quantum box. And if you then replace the half-wave guide by fast electro-optic modulators, as I showed you beforehand, you can really program all kinds of dynamics. This is one of our early results where you can see how efficient this thing is. This is really experimental results, peer in experiment compared. You see that nice ballistic spread of a quantum walk, and it corresponds to 28 step, 406 beam splitters and 29 detectors. So you see that you can have an experimental system in temporal domain, which you can control very nicely. It's a resource efficient and has an ideal homogeneity, so you can really have nice dynamics to be programmed. We explored that in several experiments over the last 10 years, implementing all kinds of different systems, starting from 2D quantum walks, graph engineering. You can study something like topological invariance, so you can do simulation which is inspired by semiconductor physics. We studied measurement dynamics or also different geometries, graph structures. One criticism we got a lot was, yes, but this is a classical interference. And it's true. The quantum walk theory for a single particle can be implemented by classical optics. And there is a second boundary to have multi-particle effects. In order to do that, we implemented recently a system where we included into this loop not only single particles, but 2 photon particles, and studied then local second and first order coherences. So you can ask how in this quantum walk, if you program it correctly with coherence, how does the first order coherence influence the second order coherence? Or in other words, if you see superposition states, what does that mean for quantum walk dynamics? And for this, we programmed the system such that the single photons were separated in space, either in the blue or the red line, and they had on the one hand exactly the same shapes. On the second case, we programmed such that there was, for the red photon, a phase shift introduced between the 2 spatial parts of 180 degrees. Now, if you do the local measurements or time-resolved measurement and ignore one of the arms, so you see the red boxes, then you get nice time-resolved homomodal interferences back. The interesting fact appears, however, if you do a non-time resolved or bucket detection effectively. So you're asking simply if the red and blue photons are interfering non-locally nicely. And then you see in the first case, because they're identical, these 2 photons superposition state, that you get a nice homomodal interference back. While in the second one, you don't get in these non-local second order interference any quantum interference. So you control nicely for the first occurrence, the second order coherence. This can be good for controlling larger quantum systems, and it shows that the photons are the main ingredients, and it's not so important how they distribute over different modes. Let me finish my talk with showing you our last experiment, which we find very exciting. And this is again about multiplexing, but multiplexing not for implementing circuits, but for state generation. And for that, I look at QA6 state generation. And this started early on. So we know how to generate QA6 states from Bell pairs, looking for double pair emissions, and have a very specific network. Now, if you ask how well does that system work, well, I bring you here an experiment again from John-Wei Punk's group from 2018, where they really succeeded in implementing 12 photon QA6 state. But what you also find is that the probability is extremely low. So we have a problem with the preparation efficiency. Why is that? Well, it is because we have to drive these parametric down conversion sources at very low probabilities. Otherwise, we have that higher photon number of contributions. And we have here an exponentially bad scaling. Now, one way to overcome that is by multiplexing. And you see it here. So you drive several of these sources. You put one of these sources in a quantum memory. And then you try it over and over again and see when you're successful. Now, we did that in the temporal domain. So we have a Bell state generator. We put one of the photons in a memory, and the other one we detect, and then we look if we store them and try it over and over again in a time multiplex fashion, and only combine them back once we have succeeded again, that we can build up QA6 states much more efficiently. This is the experimental setup for that. So basically, we have a Bell state generator and a Sagnac configuration in the loop, where there's a fast feed forward included. And these are results. So we multiplexed up to 20 photons, and we looked for the fidelity of the QA6 state generation, and we looked for 6 and 4 photon interferences. And what we find is that we can get for 6 photon QA6 state with our time multiplexing system an enhancement factor of over 35, and also for the 4 photon for 10. We believe that this is very important for the future, and see how we can use multiplexing in combination with PTC to also efficiently generate higher photon number states and multi-photon states, which we probably need for quantum communication systems. I think I'm running already briefly short over time. No. Yes.
If you need more time, go ahead. Go ahead.
Okay. So it's time to sum up. So I tried to give you an overview how we really can scale up and what is the current development in quantum photonics to get for larger systems. One important thing is temporal mode engineering. We need it on the one hand to really have reliable states, quantum pulse states of light, which we can then use in spatial networking, but we can also directly harness this temporal mode engineering to really go for high-dimensional systems. One important thing is, of course, integrate circuits. And I've demonstrated you for lithium niobate that we can have fast switching, which will be important for feed-forward or for source synchronization, and the nice reconfigurability. So I hope I've convinced you that lithium niobate is a nice platform for the future to implement quantum photonic systems. Last but not least, I showed you time multiplexing, which is yet another way to highly efficiently scale up such systems to basically achieve really also in photonics very nicely systems which we can use for large scale systems. And I showed you how the interferences, first and second order interference plays a role and how we can use this time multiplexing to also achieve highly efficient state generation. Before ending, I would like to point out that there's a whole team effort behind the scenes, and I've been very grateful to work in a great team. Here you see all the names who are really working on things. Of course, I also want to acknowledge our funding agencies from German agencies and European agencies. And last but not least, I would like to give you a vision. Where do we want to go to? We can combine all of these ideas in a single platform. So we are working on lithium niobate, but quantum photonic integrated circuits in such nonlinear materials have, I think, a great future. Here you see that you can include all kinds of different functionalities. And last but not least, I would like to advertise that currently in Paderborn, we are building up the Institute of Photonic Quantum Systems, where we are really hiring people, not only in my group, but also in different areas like in quantum dot sources or superconducting detectors. Thank you very much for your attention.
Well, thank you very much for a great talk. And then thank you. So people will be writing questions on the chat, but to start with, you showed many interesting results in the nonlinear optics part. You show Chi2 nonlinearity. What about Chi3, like Kerr? What about down conversion, up conversion, three-way mixing, four-way mixing, Raman? Can the whole spectrum of nonlinear phenomena be studied in the system you were studying before, including Raman, hyper-Raman, three-way mixing, four-way mixing, or only the ones you showed there?
Okay, so I would, in Chi3 materials are more limited. You can do sources on Chi3 for sure. I think it will be difficult to get really these bright sources, which I showed you there, simply because then you get the nonlinearity also of, as a detrimental effect, self-phase modulation, which basically drives you out of these source engineering ideas. Source engineering can be done. Now, Chi3 nonlinearities are typically much weaker. And one thing which is you can't do with Chi3 nonlinearities, as far as I know, not efficiently, is modulation. And these modulators are extremely important, as you know, or as I demonstrated. Everything, if you want to have fast modulators, fast feed forward, fast switching of bases, you will need Chi2. And this is the reason why we're concentrating on this Chi2, because you can have cleaner and more efficient state preparation. And maybe more importantly, you can also have very fast reconfigurability, which you need, for example, for feed forward. As we demonstrated in the QA6 state preparation, there a fast modulator is highly important. Don't know if that answers the question, but.
Yeah. And in principle, it could do a variety of three-way mixing phenomena and also four-way mixing, no?
Yes, you can. So you can, with Chi2, you mean, yes, you can do state transduction. So all what you know from classical optics can be done also, well, very efficiently in Chi2.
Mm-hmm. And let me look at are there any questions? I'm looking at the chat now. Let me see here. In the case, it seems where people are typing, let me, like in the Hong or Mandel interference experiment, do you see interference? Do you see like the transition between like more fermionic-like and bosonic-like in the sense that it's either bunching or anti-bunching? So it's like by changing some knob, can you go from one regime to the other one?
From bunching to anti-bunching?
Is it possible to do like because some people look at the Hong or Mandel interference as a way to exhibit more, in some regimes, more fermionic-like behavior, in other regimes, more bosonic-like behavior in the sense of bunching, anti-bunching. Do you have like a knob to be able to go from one to the other one or not?
Well, yes, what you have to do is you have to introduce entanglement somehow. So if you introduce, and we also did that in the spectral domain, entangled states, then you get from bunching to anti-bunching. That's what's always doable. Of course, you're dealing with bosons. And if you then want to have anti-bunching for more than 2 photons, it's getting more tricky. But if you're specifically interested in an anti-bunching behavior, you have to play around with these different degrees of freedoms. And for example, if you look for temporal modes which are not Gaussians, and you look what kind of interference phenomena you have there, then you find also anti-bunching behaviors if you tailored your system to a spectrally entangled state, then you can have anti-bunching.
When you go from anti-bunching to bunching, you could say it's fermionic, bosonic, but in between, you will have something which is like a crossover. It's not fully bosonic, it's not fully fermionic, but something in between. Have you looked at this kind of crossover, not to see how the statistics, somehow they get mixed, because in one case it's like bunching, anti-bunching, so it's more like fermion-like or bosonic-like. Anything in between that will give an idea, like, I wouldn't say mix statistically, you don't have anions there, but you're essentially like mixing things together. So it seemed like an exciting possibility perhaps to see if there is some signature of something which is in between.
I think we did a little bit of that in these quantum walk experiments by tailoring basically where the photons are. It doesn't matter if it's a wave function or if it's located in different positions. There you can, of course, tailor the degree of entanglement between 2 different photons. And then, yes, you can see how well they're interfering. So this interference can be controlled by controlling a different degree of freedom. And this is a possibility. I think the limitation for these things is as soon as you want to have a 3rd photon coming in, and we're looking at multi-photon states, you will lose this advantage, because then you would have to have 3 photon entanglement, and this QA6 states are, but it's getting more and more complex. Don't know if that answers your question.
I see. Oh, thanks. Like Umololu, there are questions there in the audience there?
Yes, there's a question here.
Please, I just want to know about the position you offer, if there is a website where you can go.
You can go to our web pages, University of Paderborn, SILBERHORN, you find that. Or you can drop an email directly to me. There's position offered in all access if you want what that's precisely, but you also find them on our web pages.
Thank you.